Look up at the sky, past the clouds, and 11,000 nautical miles into space. Right now, there is a constellation of 24 satellites constantly orbiting the Earth in 6 distinct intersecting planes. When you look at a GPS unit on a flight deck, it is easy to assume those satellites are beaming down a signal that tells the airplane exactly where it is located. But they aren't transmitting position data. All a GPS satellite broadcasts is a precise timestamp generated by an onboard atomic clock. For basic visual flying, using those timestamps to power a moving map is a convenient situational awareness tool. But navigating blindly through clouds under instrument flight rules requires a different standard: absolute mathematical integrity. To legally use GPS as a primary navigation source for a zero-visibility approach, a pilot has to rely on a system that masters pseudo-ranging, mitigates receiver clock error, and corrects the physical distortion of the Earth's atmosphere. Understanding the physics beneath the screen transforms a digital map into a trusted primary flight instrument. It starts with the course acquisition, or CA code. Each satellite constantly transmits this unique pseudo-random code 1,000 times a second. The receiver uses a physical equation to calculate the time interval between transmission and reception, multiplying that time by the speed of light. To measure this delay, the receiver generates an identical code, aligning its own waveform with the incoming satellite's own. The resulting mathematical distance calculation is called pseudo-ranging. To establish a two-dimensional position, the receiver needs intersecting ranges from exactly 3 satellites. Where those 3 spherical ranges overlap, you get a single location. However, a 3-satellite fix is only valid if the aircraft's altitude is already known and inputted into the system. To calculate a true 3-dimensional spatial fix, yielding latitude, longitude, and altitude simultaneously, a strict minimum of 4 satellites is required. 4 satellites complete the geometry, but this entire mathematical structure collapses if the timekeeping isn't perfectly synchronized. The satellites in orbit house multi-million-dollar atomic clocks, but the receivers built into the aircraft rely on quartz clocks, which are subject to drift. If the receiver's clock is off by even a fraction of a second, it corrupts the speed of light distance equation. When the spheres fail to intersect, you get a massive area of uncertainty. The receiver's computer identifies this timing error, then applies a trimming algorithm. It mathematically shifts the time data, adjusting the ranges until all spheres touch at one valid pixel. Through continuous mathematical trimming, the receiver eliminates its internal clock drift, forcing a standard quartz clock to operate with atomic precision. Knowing the distance to the satellites solves the time problem, but the physical placement of those satellites dictates the accuracy of the signal. Satellites clustered closely together create poor geometry, known as high position dilution of precision, or PDOP, resulting in an imprecise intersection. Conversely, low PDOP occurs when satellites are widely dispersed, narrowing the intersection into a sharp, accurate point. To ensure this geometry is safe for instrument flying, the system relies on a software function called Receiver Autonomous Integrity Monitoring, or RAIM. RAIM audits the satellite geometry. To detect an anomaly in the network, a minimum of 5 satellites must be in view. To successfully isolate and discard a corrupt satellite signal, that requirement increases to 6 satellites. This is a hard limit. If an aircraft loses RAIM integrity prior to the final approach waypoint, the pilot must abort the approach. RAIM acts as a threshold. It turns GPS from a passive listening device into a self-auditing safety network capable of supporting IFR separation. Even with verified geometry, the atmosphere is a physical barrier to accuracy. Satellite signals bend and slow down, traveling through the ionosphere and troposphere. To mitigate this distortion, the FAA developed the Wide Area Augmentation System, or WAAS. This diagram illustrates the WAAS architecture. Surveyed ground stations compare their physical location to GPS coordinates to determine the atmospheric error. The station then transmits that correction data to a geostationary satellite, which beams a real-time correction package directly to the aircraft. This continuous, closed-loop transmission compresses the standard GPS error margin from 100 meters down to 10 meters. By practically eliminating atmospheric interference, WAAS provides the reliability required for electronic vertical guidance along the z-axis during the final approach. That vertical guidance enabled by WAS led to a new classification of instrument procedures, approaches with vertical guidance, or APVs. This RNAV GPS approach plate shows a new minimums line at the bottom, localizer performance with vertical guidance, or LPV. These allow descents as low as 200 feet above the runway, with half-mile visibility, matching the precision of traditional ILS systems. Required Navigation Performance, or RNP, integrates these augmented signals with high-level onboard monitoring, requiring specialized aircraft equipment and aircrew authorization. This approach chart demonstrates RNP capability. Notice the curved track in the plan view. This radius to fix, or RF leg, banks the aircraft safely around terrain. The database encodes the exact arc radius, allowing the flight management system to perfectly fly this curve without visual reference. An aircraft can now carve a mathematically precise curve through thick cloud cover, relying entirely on satellite geometry. GPS has evolved into a deeply augmented, self-correcting spatial architecture. By mastering time and geometry, it provides the accuracy required to safely navigate the most demanding instrument environments.